Okay, so I promised you a proof of Sperner's lemma for manifolds. So, well, this is an inductive proof, like a lot of these things. So for the base case, here is the one-dimensional manifold. Remember, we have one color here, and we have another color on the other side. And basically, this is just the intermediate value theorem, which says that as you move from here to here, it changes an odd number of times. So you start out with yellow, you end up with green. Well, you can switch from yellow to green and from green to yellow. But if you switch an even number of times, then you'd end up with the same color right here. So I hope everyone believes this. Okay, so with the induction step, what we're going to do is we're going to take our manifold, and I'm going to construct a dual graph in the following way. I'm going to create a vertex for every n simplex. And then I'm going to add one more n simplex to represent kind of the outside of the manifold. So I've got one n simplex for every, I've got one vertex for every n simplex, and then one outside n simplex. Now I'm going to take my entire set of n plus 1 colors, and I'm going to throw one away. And I'm going to pay attention to this restricted set of n minus 1 colors. Of n colors. So what I'm going to do is I'm going to, whenever I find two n simplexes that share an n minus 1 face, colored with this restricted set, with the n colors, I'm going to draw an edge between them. I'm going to do the same for the external vertex. So whenever I have a boundary, a simplex, where the boundary is colored with a restricted set, the red and yellow, I'm going to draw an edge from that simplex to the external simplex. And never mind whether it's a planar. Okay, so what kinds of combinations can we have? Well, lots of simplexes will have, the vertices will have degree 0. Because here there are no edges that have the restricted set red and yellow. And so each of these has, the vertexes have even degree, because 0 is even. If I have a simplex that's colored only with the restricted colors, then I claim that I'm going to have degree 2. Because I'll take one n minus 1 face with all the colors, then the remaining one has one color chosen from there, and then that will replace, this red one will replace that one, and then we'll have two edges. So if you have only the restricted colors, then you have even degree. Suppose you have all colors, well then you have degree 1, because there's one n minus 1 face that has the restricted colors, none of the others do. And so if you have all colors, then you have odd degree. So what I've shown you is that if you look at this dual graph that I've given you, there are an odd number of n-colored simplexes. That is, simplexes that have all n plus 1. That should be n plus 1 colored. Somebody mark that down as another typo. So the number of simplexes that have all n plus 1 colors is odd. No. No. That's what I want to prove, yeah. Mark this entire slide as being broken. No, what, yeah, so I think that's out of order. So the next observation is I want to show you that the external vertex has odd degree. Okay, no, I know what this says, sorry. So this is the induction hypothesis. No, the slide isn't wrong, it's just badly designed. What I'm saying is that if you look at this face here, this is one of the m sub I, which is colored only with red and yellow. By the induction hypothesis, there are an odd number of n-colored simplexes here. So this is a correct but not suboptimally clear slide. So this is where we use the induction hypothesis. Okay, what that implies, so there are an odd number of simplexes that are colored with both red and yellow. And remember our rule for drawing an edge that says the external vertex has odd degree. So that means if we sort of summarize what we've figured out about the parity of the degrees, we have one external vertex that has odd degrees. We have some number of n simplexes with n plus 1 colors, and each one of those has odd degree. And everything else has even degree. You can probably see where I'm going with this. So every graph is easy to see. The sum of the degrees is even. Why is this? Well, every edge contributes a 2 to the degrees. So when you add them up, it's got to be an even number. So that means that there are an even number of odd degree vertices. We're doing arithmetic on mod 2 here. So in particular, we have one external vertex. The sum of the one external vertex and the number of n simplexes with n plus 1 colors is got to be even. 1 is an odd number, oddly enough. And that means that the number of n simplexes with n plus 1 colors has to be odd, and that's the proof. So it's a very simple accounting argument. So what I want to do now, so everything I've done here is, sort of elementary, combinatorial undergraduate level, fooling around with simplexes and graphs. So now I'm going to relate this to distributed computing and show you that no manifold task can solve n-set agreement. Remember, where n is n plus 1 processes, and n-set agreement means they agree to discard one value. And so we'll assume that a protocol exists by way of contradiction. So I'll run the manifold task protocol, and everybody ends up at a vertex on the manifold. And then based on where you are, you choose your value. And so the idea here is I'm going to color each vertex with the ID of the winning process. So if I pick my value, then I color that vertex with my value. If I pick someone else's value, I color the vertex with their value. And so what that looks like is we have our manifold protocol. And here, instead of coloring each vertex with the process whose view it is, we color it with the process that wins the consensus. So that means we're using the colors here in a slightly different meaning than we did before. And I'm going to argue this is a Sperner coloring. Why is this? Well, here, if P runs by itself and finishes before anyone takes a step, then only P can win. Here, only Q and R run, so only Q and R can win. So this is a somewhat more informal argument than I did before, but since we've gone through this enough times, I think it's a good idea to not dwell on this too much. No, in this one, everybody picks red's value. So here, this is where red runs by itself. This should actually be, that should be a different value, I think. No, they are different values on the screen. One is brown and one is red. So, I will fix that. So this is brown and this is red. Remember that. And it doesn't matter what these are. But yeah, that's another slide that needs to be fixed. So this is a Sperner coloring, and that says that there's some simplex in here that has all 3 colors. And what that means is that there's some execution where we have n plus 1 winners. But the definition of set agreement is that there are fewer than n plus 1 winners. And so that's a contradiction. So it says that if your protocol complex is a manifold with boundary, then you can't solve k-set agreement. And that's comes from the definition of the fact that this corresponds exactly to doing Sperner colorings on the manifolds. So that's the proof there.
What's the meaning of more than one winner?
Everybody runs and you choose somebody's value. And if I choose somebody's value, then they're the winner as far as I'm concerned. Now, the restriction is, in consensus, everybody has to choose the same value, so there's exactly one winner. But in k-set agreement, it's okay if you choose k distinct values where k is small enough. So a two-set agreement, it's okay if I choose one value, if I choose 0 and you choose 1, as long as everyone else also chooses either 0 or 1. And as far as I'm concerned, the winner is 0, and as far as you're concerned, the winner is 1. But this is the winner with respect to somebody's view. And so what we're saying here is that there's some execution. Each simplex here is the outcome of some interleaving, some execution, where everybody chooses a distinct value. But the goal of the algorithm is to not choose all n plus 1 values, is to choose a fewer. But any way you can plausibly choose values turns out to be a Sperner coloring, and so then there's got to be some execution. No matter how clever you are, there's going to be some execution where you choose too many values.
The color, what does it mean?
This means that the process chose the blue process's input.
Because before that you used colors for...
This is true. Before I use colors to say who it was who was doing the choosing, here I'm using the colors for a different purpose to mean which value you choose. And you're right, it is a little confusing. Maybe I should change the shape of the, change it to squares or something just to, but it's hard to resist using colors for this sort of thing. Okay, so in the roadmap.
So maybe some kind of, I don't know, wrap up or just like you've just finished to prove something that, as you said, was open for a long time. So
Yes.
like actually 6 years, but
Yeah.
who counts?
So this result that you can't do k-set agreement was proved simultaneously by 3 papers at a stock. So there's a paper that Khagit and I wrote, which is basically, this is the descendant of that. There was a paper by Eli Goffney and his student Elizabeth Borowski, where they used graph theory, which was actually simplicial complexes expressed in terms of graph theory. They talked about cliques instead of simplexes. And then there was a paper by Michael Sachs and Fotis Zaharoglu, where they used point set topology and something sort of like the Brouwer fixed point theorem, which is kind of like Sperner's lemma, except in a continuous way, to prove the same result. Ellie and Mike and company were the ones who invented the immediate snapshot model. So that appeared under different names in both of those papers. We didn't use that. The notion of manifolds didn't show up in any of this explicitly, although the use of Sperner's lemma is kind of implicit use. So the whole point of writing this course was in some sense to take all this machinery and turn it into something where you could present it in a class like this, because those papers are not something where you'd want to present it in a regular class, unless it's one of these seminars where everyone puts helmets on before they and takes shovels to try to get to things. But on the bigger picture, what we've done is shown that this k-set agreement, which is defined entirely in terms of kind of algorithms, in terms of executions unfolding in time, first you do this and then you do that, that one way to deal with it is to, again, use this formalism based on simplicial complexes, where we cast everything into these static mathematical objects. Sperner's lemma does not talk about executions. It doesn't talk about time. In some sense, we've frozen all of the possibilities into one kind of combinatorial object, and we can reason about that thing as a whole using this combinatorial machinery. And of course, we didn't prove Sperner's lemma. Sperner did it sometime in the 30s. And so as I keep saying, the other advantage of using this kind of approach is that you can build on a lot of earlier work, and you don't have to reinvent the wheel. I think reinventing the wheel is one of the plagues of certain areas of distributed computing. Okay, so I'm going to introduce another problem. And what I'm going to do here is I'm going to show you a separation. I'm going to show you two problems where one problem, but the two problems look completely different. But in fact, one of them is strictly more difficult than the other. And I'm going to show you a reduction from one to the other, and I'm going to show you a counterexample of a computational model that is capable of solving one but not capable of solving the other. So this is something called weak symmetry breaking. So this is another problem that might seem like it's a little bit artificial, but in fact it turns out to be a very natural problem when you're looking at a problem we'll look at in detail later on called renaming. So this is a kind of a reduced form of that problem. And the idea here is that we have kind of a black box. We have a bunch of processes that come in and they access the black box. And we want them to split into two groups, which we will poetically call group 0 and group 1. And the rule is that if everybody shows up, if they all participate, then at least one process goes into each group. So we break the asymmetry. We send them into separate groups. The reason this is weak is that if fewer participate, if they don't all show up, then we don't care. It's okay if they all go to the same group. So we only need to worry about what happens if all n+1 processes participate. If one of them fails, then we don't have any requirements for what happens. So you can see why this seems like it's pretty weak. We want to rule out trivial solutions to this. And so, one difficulty with posing these problems is there's always a temptation to do what's called model abuse and say, well, there's an easy way to solve this. It's like solving NP-hard problems using NP-RAMs by doing, putting arbitrary number of bits in, things like that. So a trivial solution is you choose the parity of your ID. And that's easy to implement constant time. And so, that's not much fun. So we want to rule that out. So what we really want to say is that any protocol should be anonymous.
You assume that the ideas are from 1 to n.
Yeah. So,
Either or either.
well, that's one way out of it. But you could say, well, their IDs might come from a really big space, and you can't do that. But then, this is another way to break out of that. And so what we'll say is we want this to be anonymous, and the output depends on your input value, and it depends on the interleaving, of course, but not your ID. So in other words, if I take an interleaving and I change all the IDs, then everybody still then the outputs remain the same. So this is a technical requirement that we need in order to avoid model abuse like that. And this is a restriction on the protocol, not the task. The task makes perfect sense even if you're allowed to cheat. But we're saying we're not willing to accept any solution to the task that says, well, if my ID is a prime number, then do this. And so what I want to do is I want to show you that weak symmetry breaking and case-state agreement, that there's a separation between them. So what I'm going to do is I'm going to construct a manifold task that solves weak symmetry breaking. Now, we've seen that manifold tasks cannot solve n-set agreement. And that will give us our separation. Now, the manifold task that I'm going to put together is a little bit artificial in the sense that it exists only to prove this point. So this is not something that is likely, Intel is not going to start selling a machine that has hardware instructions that do this sort of thing. And you'll see why in a second. But it does show us that there, in a mathematical sense, that there's a separation between these problems.
Manifold task or manifold protocol?
Same. I'm assuming if you have a manifold task as a black box, then you solve the manifold task and all you have is your output, and you treat that as a protocol complex.
Did you define what the manifold task is, or is this?
It's a manifold protocol. Yeah, I should be clearer about that. So manifold task is one where the output complex is a manifold. And then I'll give you a black box that solves this, and that turns it into a manifold protocol. But you're right, I should be more precise about the distinction. So I'll give you a black box that takes an input and gives you back an output complex that's a manifold. So you end up getting a vertex in that, and everyone else gets a vertex on the same simplex, and then you try to solve your problem based on where you ended up.
Why do you say it's harder? You show some model in which this can be solved, this not?
Yes.
But some other model in which this can be solved, this not.
But there's a subtle point. I'm going to show you a reduction from one to the other. So that shows that in almost any model, unless you get into really pathological cases, if you can solve one, you can solve the other. And then I'm going to give you an example of a model where there's a separation. You know, there's certainly models where you can solve both of them, or neither. Okay, so behold a simplex. And remember that this is what the standard chromatic subdivision looks like. So we're going to we're going to work with the combinatorial definition again. So never, the picture is just there to help you visualize what's going on. But we need to navigate around this a little bit. So what I'm going to do is I'm going to take 3 of these. So this is the 3-process version. I'm going to give you the n-process version in a minute. So I'm going to build a manifold protocol by taking 3 copies of the standard subdivision. I'm going to glue them together along these edges, and notice that the process IDs are the same along here. So it's okay to identify these edges. Then I'm going to go to the outside edges, and I'm going to glue them together along here. And the result is a manifold complex, and I'm going to posit the existence of a black box that gives you this. Does this look familiar to anyone?
Maybe.
Beg pardon?
Maybe.
Yep. So it's a Mobius strip. Of course, when I show you the higher dimensional versions of this, it's not going to be a Mobius strip, but it will be a non-orientable manifold. So this is a manifold task. If you look at the boundary, this is a Schwerner coloring. So this is a manifold. Every edge is contained in 2 triangles. There's a boundary here. These are internal. And there's a Schwerner coloring on the boundary. So this is all red and blue. This is all blue and yellow. And this is all red and yellow. So this is a manifold, and a manifold with boundary, and I've given you a Schwerner coloring with the process IDs. So in order to go further, we need to navigate around these things a little bit, so I'll define some more terminology. So each face of this subdivision has a central simplex. So the one-dimensional central simplex are these 3 things here. And 2-dimensional is this one here, and you can imagine how it goes in higher dimensions. What would be ha simplex ha merkaz? Merkazi. Okay, then when we look at the the faces of the triangle, the way we've subdivided them here, we'll call this one the external, because that's part of the boundary. And we'll call these the internal, because they're glued to another simplex. So this is the terminology we'll use when arguing about this.
What's the difference again?
Oh, so when I build this thing, I glue 3 of these copies, 3 of these things together like that. And so the edge of this simplex is actually glued onto another one, so I'll call that internal. This one is actually a boundary of the whole of the Mobius strip, so I'll call that external.
I'm talking the edges.
Yes. Yeah. This is these are external simplexes, and these are internal simplexes. So now what I'm going to do is I'm going to give you a black and white coloring that solves the weak symmetry breaking. So to solve weak symmetry breaking, you have to have no monochromatic simplexes, and no monochromatic triangles in this case. Monochromatic edges are okay because we don't care what happens if 2 processes are run. But if 3 of them run, then they have to split between 0 and 1. So that means there's no, we have to have both black and white colorings, black and white colors on the vertices. And it has to be symmetric on the boundary in order to be anonymous. So the central 2 simplex of this face, I'm going to take the vertexes near the external face, and I'm going to color that white. And I'm going to take the rest and color them black. Then on the central simplex of the external face, I'm going to color that black. So it looks like this. And everything else, I'm going to color white. So this is what the coloring looks like. And you can look at this and convince yourself that there are no monochromatic simplexes. You can convince yourself that it's symmetric on the boundary. Each piece of the boundary has the same coloring. Yeah. But this piece of the boundary and this piece and that piece are all symmetric. So if these two, any execution with these two processes is indistinguishable from those 2 processes. So it's anonymous. So you couldn't have used your process ID because you get the same thing no matter what. So there's a little bit more technical definition hiding there that I'm going to skip over. But basically, if this were not symmetric, then it might be that if these 2 run, you get all white, and if these 2 run, you get all black. But that doesn't happen here. This is a proof. This is a proof that for 3 processes, the Mobius task solves weak symmetry breaking.
Where is the proof here?
So I want to solve weak symmetry breaking, which says that I run this protocol and then I join group 0 or group 1. And if everybody runs, then somebody goes to 0 and somebody goes to 1. So what I'm going to do is I'm going to run the protocol, and I'm going to everybody ends up on some simplex here. And I'm going to look at the color of my vertex and use that to choose which group to join. So if I end up with a white color, I'm going to join a 0, and if I end up with a black color, I'm going to join 1.
And you showed what happens to a simplex, but what happens to a bigger manifold?
There's no input here. I just join the protocol, and depending on how many, because it's anonymous, it's non-trivial. So if 2 processes show up, then we don't care what happens, but whatever they decide can't depend on their IDs. And
So you don't repeat the game again?
no. In this case, we just run it once. I look at my color, and I join a group based on that color. And
And no matter why you do it once,
so I did this. So this is a contrived problem that exists only to show that because this is a manifold, I can't solve 2-set agreement with this.
but why? You say that the simplex of the complex of the protocol
Yeah.
has the shape of Möbius?
Yes.
Why?
Because that's how I defined it. So this example exists to show that if I gave you such a thing, you go to the hardware store and I pull out a black box that solves this problem, and I could sell it to you saying, well, this will solve the weak symmetry breaking, but by the way, it cannot solve 2-set agreement.
So you're designing this.
Yeah. So I designed it this way because I want to show that there is at least one model of computation that solves one problem but not the other. So that says that 2-set agreement is harder than 3-process weak symmetry breaking. Because here is an object that solves, a gadget that solves one problem but not the other one. Yeah?
I think that's what Hagit asked earlier, but how do you know there's even a protocol that corresponds to this?
There doesn't have to be. If I could build a hardware box that solves this. I just hide the details. So it uses compare and swap and test and set. Maybe it solves a much more difficult problem, but then it hides everything and just gives you comes back with the number of the vertex, and then you look up in the book to see what color it is. So I didn't say that this, again, I didn't say this is a practical problem of compelling urgency. Intel is not going to pay $1 million for the right to use this. But it just shows that here's a mathematical object that solves one problem but not the other. Therefore, there's a separation. And the fact that it might not be entirely natural doesn't matter in this context.
So somehow, the model means that somebody somehow, Intel for that, in your example, guarantees you that you will just have these particular set of executions.
Yes.
In some set.
Yeah, yeah. Yeah, these are the only executions that can happen. How you reduce this to transistors is not our problem because we're theoreticians. But it would be clearly possible to do so. And so you think of this as a kind of a black box where I press the button saying I want to participate and I get back a vertex. And these are the only possible vertices. Each simplex represents a possible 3 vertices that can be returned.
Where to use the assumption that if you have less than n processors, then you don't care about your output?
Because if we have, say, 2 processors in this execution, then they both join group 1. So on the edge here, this represents an execution where only 2 processes participate, and here they both go to group 1. But that's okay. But if the third one comes along later, then it goes to a group 0. So all we care about is that there are no monochromatic triangles. Monochromatic edges are perfectly okay.
So they did that does it count and choose one simplex and then the processors need to somehow that's the way to see it.
Well, so the processes go to the black box and they choose a vertex, and we hand you a little book that says that if this is the vertex you choose, this is the color. So
the vertex they choose must be
some triangle. Yeah, either an edge or a triangle. Yeah. So it's non-deterministic, or you don't know. It might be deterministic depending on the time with electromagnetic fields or something. But you press your button and then you end up with a vertex, and everybody ends up on some simplex. And then if you choose your color, then that solves a weak symmetry breaking. But because it's a manifold, it doesn't solve a set agreement. So that's, so you can see that every simplex has both black and white colors, and the boundary coloring is symmetric, which is basically the same as saying it's anonymous. And there we are. So then I have the general construction, which, what time is it?
We have 5 minutes.
Okay, so I'm going to blast through the general construction just to show that it can be done, but I don't think it's all that interesting to see all the details. So basically, in general, what you do is you take n+1 copies, you take the standard chromatic subdivision, you take n+1 copies. These are not actually tetrahedra, they're higher dimensional, and they're subdivided, but the subdivision doesn't look like that. So these are just symbols intended to be suggestive. And so what I'm going to do is I'm going to look at the ith one and tell you how to glue it to the rest. So here I have all of the ones except for I. So what I'm going to do is I'm going to say the ith face of the ith complex is the external one. Again, this is all bookkeeping, and don't worry if you don't understand it. I just want to convince you that we've thought about it. By the way, this only works for even dimensions. So we have 2n others. So there's a 2n+1. We pull this one out, and we have 2n+1 others. So I'm going to take face j here, and I'm going to glue this onto face j of this one here, where that's the rank j plus n out of 2n. Okay, so why this magical formula? Well, simply because we want it to be symmetric. So if we exchange places, then we glue the same edges together, depending on how you do this. And that explains why it's a manifold. In fact, it's a non-orientable manifold. It also explains why it works only for even dimensions. Open problem is, can you generalize this to odd dimensions? Maybe the result isn't true for odd dimensions. I don't think it. Because if you take that definition, then it's not a manifold in odd dimensions, only in even dimensions. Because my formula for gluing one thing to the other isn't symmetric anymore. And so you end up gluing too many things together. And then if it's not a manifold, then we can't use it. So open problem is, can you do this for other dimensions?
So basically, what is you've shown us a specific manifold
Yeah.
that can be colored black and white in
Yeah,
a way
yeah.
consistent with weak symmetry breaking.
Yeah, yeah.
But cannot be colored.
Consistent with,
some
yeah.
colors.
Yeah.
Cannot have a Sperner color.
Yeah, 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 exactly.
It has a weak symmetry breaking coloring, but not a Sperner.
Yeah, yeah, yeah. So I'm not giving you a sweeping proof of big classes of objects. I'm showing you here is a particular thing that separates the two problems. So the black and white coloring we pick is basically the same that we did before, except generalized to higher dimensions. When we talk about the external faces, we need to talk about the central vertices in multiple dimensions. And again, I'm not going to go over this in detail. It's in the notes if you really want to see how it works. And then everything else is white, just as before. And then this time, instead of showing you the picture, you have to actually argue there's no monochromatic end simplexes. And so you just do a case analysis. The central one is, by construction, not monochromatic. If you're not central, then you have to intersect one of the faces. If you intersect the internal face, then you have to hit the center and white at the edge, so you're not monochromatic. If you hit the external face, then you're white at the center and black at least one of the other centers. So nothing difficult here. So what we did here, so what we've done so far is I've shown you this separation. That given the Mobius task, I can solve weak symmetry breaking, but I know I can't solve a set agreement. So the next step is to show that if I have a box for anonymous set agreement, then I can solve weak symmetry breaking. So that's the reduction going the other way. So this just says that there's something that separates it, but it could be that these are incomparable, that neither one solves the other. But the next step is to actually give you a real live algorithm that does this. And so I think I'll postpone that till next time, just out of since we've covered a fair amount of material. And the one thing that I'll mention is that what we've done so far is looking at combinatorial things basically to show stuff you can't do, separation and impossibility. What we'll do next time is I'll show you an actual algorithm to show that what we can do. So combinatorial approaches are good at things like separation and impossibility, but it's not impossible to show that algorithms exist using it, but it's a little bit cumbersome. And the simplest way to show that an algorithm exists is to show you the algorithm. And so there's a kind of a complementary thing here where the lower bounds you can use topology, but upper bounds, the easiest way out is to actually do the damn algorithm. And that's what we'll do next time. Thanks.